So yeah, thank you for inviting me here. Thank you for coming also. So this is about probabilistic inference in simulators. But basically, what we do is to treat existing stochastic simulators as probabilistic programs. Yeah, I'm going to show you what that means. So I think it is well known to this audience that simulators are very important in current state of the art in scientific research. So this applies to many scales ranging from particle physics to weather simulations or cosmology. So in this work, we bring two fields together. One is probabilistic programming and one is simulation. These are closely related, but until today, there was no way to treat simulators as probabilistic programs. And in this work, we are providing some infrastructure that allows you to do that. So I got this the inspiration for the slide from Gilles. Maybe if you were here in the first talk of the day, he had this like a black box picture of a simulator, and with latents inside the simulator box and parameters going into that. So this is kind of the same thing. So a simulator is Gilles is here. So the simulator is a piece of software that takes some set of parameters and gives you some instances of a simulated event. So as Gilles was talking about briefly in the morning, so you could do two things with this. One is called prediction, and this is this basically means running the simulator forward. You simulate the forward evolution of your system, and you generate some outputs of samples of output. This is interesting and useful for cases of forecasting or doing projections, like people doing climate science or economics or like flood modeling. But in science, most of the time we need the inverse. We just need to do inference, and it means to figure out the parameters that can produce an observed output that you have in your hand. This is often a manual process and it's difficult. So some examples of this is like, for example, you have an understanding of how a gene network can produce some gene expression. You have a forward understanding of this, and someone gives you a gene expression data, like on the right-hand side, and you are trying to infer what types of networks can give rise to that expression data. Or in the field of seismology, you have a very good understanding of how seismic waves propagate in media. So you have a forward simulator of this, and given some seismometer readings, you are trying to infer earthquake locations or characteristics. And I've been doing this sort of collaborations in the field of particle physics, and the idea is to eventually have some detector readings. And doing this sort of inference, you are after performing event analysis on new particle discoveries. So I don't have much time to go into detail, but maybe some of you have heard of this new machine learning subfield called probabilistic programming. It's basically a machine learning framework that allows you to express probability models using general purpose programming languages. And these frameworks give you an automated way of performing Bayesian inference in the model you specify as a program, conditioned on some observed data. People know about Pyro, Edward, or Stan, like this sort of existing libraries. You may have heard about them. The situation with these libraries is that they have been limited to toy and small-scale problems. This is something that's been running in the probabilistic programming community. And they normally require you to implement probabilistic model from scratch using a chosen library or language. So this precludes like large-scale scientific problems, because you cannot just sit down and implement the standard model, I guess, in Pyro. I know some people are attempting to do something similar to that, but so the key idea in this work is that many simulators are stochastic, and just by being stochastic, they already behave probabilistic. If you have some infrastructure to treat this stochasticity as a sample from prior, so you can treat stochastic simulators as probabilistic programs. That's the key idea. So the simulator is not a black box. You have the code for it, and you can interface this code with some sort of infrastructure to treat the simulator code as a probabilistic program. And so we just need the infrastructure to execute simulators as probabilistic programs. So I've been working on this code base. Now it has a name, so we started to call it phiprobe and like made a logo and things. So I'm just trying to develop this currently. It's in alpha stage. We will provide a website and tutorials and examples of like if you have an existing simulator that is stochastic, how you can just go about connecting that to the system in order to treat it as a probabilistic program. So it's a new probabilistic programming system for specifically for existing stochastic simulators and working with them. So I will try to explain very briefly how this works in practice. What you do in probabilistic inference in this way is you run your simulator forward. Actually, it's the only thing you can do with the simulator. It runs forward. There aren't a lot of other options. So you have a way of running simulator forward many times, and you catch all the random choices in the simulator. And these are recorded in an object called an execution trace. So this is supposed to represent that. And because we are in the general purpose programming setting, every execution can be of different length. So this is what this is supposed to represent. So these are random number choices, and their values and locations in the code, you record them, and you record the corresponding output for one execution. So this is called a trace object. And core part of the system is this probabilistic programming execution protocol. It's like a infrastructure that allows you to catch the random number calls in these languages that it supports. So it supports most of the languages that would matter for a science community. So using this, and there are also some extra details, like we need to uniquely identify or label all the random number choices in the simulator. And this is done automatically again for using the same protocol. You get a unique label that is based on basically stack frames in the programming system. This is how one such address looks like in a C++ example. Yeah, so you have this capability of recording execution traces, running things forward. And the second thing is to do conditioning. Conditioning just means a comparison between observed data and simulated output in each execution trace. So somebody gives you an observed data, and you run your simulator many times forward. And in each time you make a comparison between this simulated output and the observed data. And you make a judgment of how close these things are. It is very similar to what Jill was talking about in the morning with the approximate Bayesian computation. But there is no hard acceptance criterion. You basically have a smooth likelihood, like that measures how close do you match the observation. So by doing this conditioning, you can approximate the distribution of parameters that produce your given observation. And it is Bayesian, and you get the posterior distribution over all the simulator execution. So, because we introduced this capability, we end up with giant probability models. When you work with simulators, if the code base is large, you end up with the simulator with like basically endless number of latent variables. In practice, like tens of thousands of latent variables. And we need to run this millions of times. And the simulator execution and MCMC inference are sequential. And we have problems like burn-in and autocorrelation in MCMC. So there is some computational cost to doing this. But we can amortize this cost using this deep learning. Basically, we have an amortized inference scheme that allows you to do this type of inference in an existing large simulator using a bit of deep learning. And so this is an attempt at explaining how that works. So basically, you run your simulator, potentially many instances of it in a distributed way, and you record these execution traces, and you have a pool of execution traces recorded. And from this, in a potentially distributed way, you train a neural network, and this neural network is based on LSTM. It's a recurrent type of neural network. And the idea is that the output of your simulator in each execution trace becomes the input to your neural network, so that the neural network, with enough training, it has an idea of, like, given any observed data or observed event, it knows to predict the rest of the trace that would give rise to this type of event. So you do this training, And the neural networks are a bit complicated in structure. I don't have time to go into detail, but because of the open-ended nature of the simulator execution, these neural networks are dynamic. And layers get created as we learn more parts of the simulator. And it is costly, but it is amortized. Amortized means that you have to do this type of thing only once for a given model. And you end up with a trained neural network that you can use later on for inference in a fast and efficient way. So you get your trained neural network at the end of all this. You're just left with that. And you do inference with this. So there are so the way it's done is like we have the trained neural network. Someone gives us at inference time a new piece of observed data. We put these things together, and we run many instances of this neural network in parallel, given the observed data as input to these, and predictions of simulator latents are coming out of the neural network, and we execute the simulator with these random number choices. And this gives you a collection of traces. And these traces correspond to a posterior distribution in a Bayesian setting, conditioned on this observed data. And there are many advantages with this, but there is nothing like a burn-in, or there is no autocorrelation, because like basically each run of this neural network corresponds to an independent sample from the approximate posterior. And yeah, so another way sometimes we show this is so you have the probabilistic programming or machine learning system here on the top, and you have the simulator in the bottom. This thing acts as a puppet master. So given some observed data, the machine learning system has the ability to control or guide the simulator in ways that would produce this type of data. So this is how we explain this. Yeah, so this software that I've been working on is available currently, like it's public. So we are just writing the website and documentation for this. Yeah, so all these things started as a collaboration between physics and machine learning and HPC people. So you may recognize some of these people, I'm sure. Gilles is with us. So the idea was to, like the eventual goal for something like this is to get some real data observation from a particle physics detector, and we will work with a full forward model that you implement as a particle physics like a prior model, and we will do some Bayesian conditioning and get posterior over the simulator latent space from which you can do interesting things that you cannot do currently in particle physics. So we are working towards this, and we had some initial proof of concept results proving that this type of thing can work. So we looked at a tau lepton decay event, and so we worked with the Sharpa simulator, and so this simulator address space looks something like this. These are two examples of that, and we discovered, like during I think we ran the simulator maybe up to tens of millions of times, and we ended up discovering around 25,000 latent addresses, unique addresses. So it has at least this many addresses for this problem implemented in Sharpa, but in practice, it's an unlimited number of addresses because this is a Turing-complete system. It's in C++, and there are loops in it, and there are control flow is influenced by what is sampled. So theoretically, this thing defines an unlimited, like infinite probability model. So you cannot say it has this many latents. Yeah, so in the paper, we have some posterior results. So we achieved the first tractable Bayesian inference over LHC physics expressed in this type of latent space. Yeah, 5 minutes. So it had terrible autocorrelation. It's like a typical autocorrelation time is like in the 10,000 iterations in MCMC inference. So using this amortized inference scheme, so we in one example that we have in the paper, we got like a 200 times speed up, something like this. In the paper, we had like an MCMC baseline result that took 115 hours to get. And we trained that neural network, and we got the same comparable result in 30 minutes. And this is embarrassing in the parallel. You can, like, if you have more compute, you could get this number even down to like seconds. And this is like basically showing you these two posteriors line up. So that is our proof of concept, that is, we can do this. And the interesting thing here is this extra detail that, so you get a posterior over everything in the simulator space. So for example, in these plots, we have the tau particles, momenta, and other things about it. So all these things are somewhere here in the simulator's latent space, but there are all the other things that happened in the simulator so that you can, again, go to your posterior results and ask questions about like what happened in the simulator, what part of the simulator was running, and you can basically analyze things in a way that was not possible before. Yeah, I think I don't have much time to go into detail here, but this is a plot where we look at like trace executions. These are like random number samples, and these loops you see here, they correspond to loops in the rejection sampling code in Sharpa. They are literally loops that do some samples until some acceptance condition is satisfied. And the center of the thing is like the base probability model. So we are looking at this type of things. And we have a running joke. I wasn't sure if I should do this today, but yeah, why not? So yeah, this thing started with me showing this type of plot one day. I think it was in Trieste, Visual, in the Dark Machines workshop. So someone tweeted saying this is like the largest number of plots in the presentation. Then Lucas Heinrich, one of our key collaborators, he started this tradition of like showing the same plot, but putting the tweet about my plot next to it and saying he doubled the record because he has two things. Then I did that again, then he did that again, then I did that again. I think we are like in depth 5 thing at this point. It's kind of silly, but yeah, here it is. Yeah, I would like to finish by showing this. So this is another way of looking at this type of difficult to interpret thing. So this is very complicated and difficult to look at because it shows you like every node here is a sample. There is another thing to look at the same thing. So this same thing collapses to this thing if you modify your addressing scheme a bit. So for example, this thing shows you the start of the execution. This is the end of the execution. So this shows you these are like random number samples that can happen in this location in the code. So all these things are always following each other. Here you can either go here or sample yourself again, or like you can have like cycles, you can have different choices. So this is like showing you how latent samples follow each other in the code base. So this is the picture you get when you look at the 10 most frequent types of executing your simulator, Sharpa. And yeah, these correspond to addresses in the code. And you can identify these things. So all these labels correspond to places in the code base. So you can go there and see what is going on. So the interesting thing is if you look at a bigger number of trace types, you get a more detailed picture of the same thing. And as you look at more and more trace types, you literally uncover the latent structure of your simulator code base that is already there in the code base. You start to see the picture of like what is happening here as a probability model. So we think this is very interesting, and you can do many interesting things like learning a surrogate model on top of this structure with some sort of message passing network, for example, or you get also posterior plots of this type in your posterior results. Yeah, basically these types of things that we are working on. These rejection sampling loops are very problematic. It's difficult to handle in probabilistic programming. Basically, we are working on that. And there are some students in several research groups working on applications of the same thing in different simulators. Yeah, so this is where we are. That's it.
Questions? So you applied this to tau decay, right? Could you also imagine doing this for the whole event in a collision?
Yeah, I can imagine, yes.
What would be the limitation there?
Compute, I think. And also this like the rejection sampling idea, this is something we are currently investigating. There are like, it's difficult to handle rejection sampling loops because they mean like thousands of samples. It is something that was not handled by the probabilistic programming community until this, because like they were really working with really small scale problems. So we really need some innovation in the probabilistic programming inference engines to support that type of thing. It's like a very big compute bottleneck. Yeah.
Other questions? Michael.
So when you're tracing the flows of this random numbers through the whole program,
Yeah.
are you're kind of counting you're only doing basically counting experiments, or do you keep track of like Jacobians of each transformation of every random variable?
At this point, this is not differentiable. Like this is like we interact with the simulator only in a non-differentiable way. We just have a record of what was the prior distribution at that point, what was the number sampled.
Yeah.
That's all we know. There is no Jacobians or anything. But if you have a differentiable simulator, you can still do this type of thing. Actually, one of the things in this list that I failed to mention is like, it's the first thing here, autodiff through the protocol. So we can have like a differentiable prior, and we can do like gradient-based inference in this and stuff like that. So it will be super exciting.
Okay. Okay, so let's thanks again, Güneş.
All right. Thank you.